In the darkest corners of our universe lurk cosmic monsters of unimaginable power, objects so extreme they bend the very fabric of reality itself. Black holes, where gravity reigns supreme and the laws of physics are pushed to their breaking point. For centuries, these gravitational behemoths existed only in the minds of visionaries. From John Michell's dark stars in the 18th century to Einstein's revolutionary equations that predicted their existence, black holes have journeyed from mathematical curiosity to confirmed cosmic reality. Now, in 2025, we stand at the frontier of black hole science. With breakthrough technologies and observations revealing their secrets like never before, I invite you on the ultimate journey into darkness, a comprehensive exploration of the most terrifying and awe-inspiring objects in existence. Black holes are not merely cosmic oddities, they are architects of our universe, shaping galaxies, triggering star formation, and potentially holding the key to understanding the fundamental nature of space, time, and gravity itself. From stellar mass black holes born in the violent death throes of massive stars to the supermassive giants lurking at the centers of galaxies, some devouring matter with the brilliance of a trillion suns, these cosmic engines challenge everything we thought we knew about the universe. Imagine an object 66 billion times more massive than our Sun, with an event horizon larger than our entire solar system. Ton 618, the most massive black hole ever discovered, stands as a testament to the mind-bending extremes that exist in our cosmos. What happens when you fall into a black hole? How do these invisible monsters warp space-time? Can information truly be destroyed? And what secrets might they hold about the ultimate fate of our universe? In this definitive exploration, we'll journey from the birth of black holes to their most extreme manifestations. We'll witness the cosmic dance of binary black holes, explore the mysterious singularities at their cores, and confront the profound paradoxes they present to modern physics. Prepare to have your understanding of reality challenged as we venture beyond the event horizon and into the shadows of infinity. In this documentary, you will discover how supermassive black holes control the fate of entire galaxies, the shocking truth about what happens when you cross the event horizon, mind-bending paradoxes that continue to baffle our greatest physicists, revolutionary new theories that could redefine our understanding of space and time, the ultimate cosmic question: could black holes be gateways to other universes? Join us as we journey to the edge of human knowledge and beyond. In the vast expanse of the cosmos, amidst the swirling galaxies and shimmering nebulae, lurk objects of immense power and mystery, black holes. These celestial entities, once relegated to the realm of science fiction, have captivated the imaginations of scientists and stargazers alike for centuries. Their gravitational pull is so strong that nothing, not even light, can escape their grasp, rendering them invisible to the naked eye. Yet, despite their elusive nature, black holes have emerged as some of the most studied and awe-inspiring objects in the universe. Black holes challenge our fundamental understanding of physics, pushing the boundaries of space, time, and gravity. They are born from the death throes of massive stars, collapsing under their own weight to form infinitely dense points known as singularities. These singularities are shrouded by event horizons, points of no return beyond which the fabric of space-time is irrevocably warped. The study of black holes has revolutionized our understanding of the cosmos. They are no longer seen as mere cosmic oddities but as integral components of galactic evolution, influencing the birth of stars, the dynamics of galaxies, and the very structure of the universe itself. Their existence has forced us to confront the limitations of our current knowledge and to seek new explanations for the workings of the cosmos. The concept of black holes has been pondered by scientists and philosophers for centuries. As early as the 18th century, John Michell, an English natural philosopher, proposed the existence of dark stars, massive objects whose gravity could trap light. Similarly, French mathematician Pierre-Simon Laplace independently formulated the idea of celestial bodies so dense that their escape velocity would exceed the speed of light. However, century, with the advent of Albert Einstein's theory of general relativity, that the true nature of black holes began to be understood. Einstein's groundbreaking theory revolutionized our understanding of gravity, describing it not as a force, but as a curvature of spacetime caused by the presence of mass and energy. Einstein's equations predicted the existence of objects so massive and compact that they would warp spacetime, creating regions from which nothing could escape. These objects, initially met with skepticism, would later become known as black holes. In this documentary, we embark on a captivating journey into the heart of darkness, exploring the history, science, and mysteries surrounding black holes. From the early speculations of dark stars to the groundbreaking discoveries of gravitational waves and the first-ever images of these enigmatic objects, we delve into the captivating story of black holes. Our exploration will take us to the edge of the observable universe, where we will witness the awe-inspiring power of black holes as they shape galaxies and warp the fabric of space-time. We will journey to the event horizon, the point of no return, and peer into the abyss, seeking answers to some of the most fundamental questions about the nature of gravity, the fate of information, and the ultimate destiny of the universe itself. Join us as we unravel the secrets of these cosmic enigmas, venturing into the shadows of infinity to uncover the profound implications that black holes hold for our understanding of the cosmos and our place within it.
Imagine a time before the roar of rockets, before the glow of electric lights, a time when the universe was understood through the lens of telescopes pointed toward the heavens and the elegant equations scribbled in dimly lit studies. It was in this era, the late 18th century, that the seeds of a radical idea were sown, a concept so bizarre and audacious that it would take centuries for science to catch up and confirm its reality. This was the genesis of the black hole. An object so dense, so gravitationally powerful, that it could trap light itself. The very notion of a dark star, a celestial object that could devour light, seemed more at home in the pages of a Gothic novel than in the annals of scientific inquiry. Yet two brilliant minds, separated by miles and circumstance, would independently stumble upon this perplexing possibility. Their names were John Michell and Pierre-Simon Laplace, and their ideas, though nascent and incomplete, would lay the groundwork for one of the most profound revolutions in our understanding of the universe. Their journey into the darkness began not with telescopes or observatories, but with a simple yet profound question: what is the nature of gravity? At the time, Sir Isaac Newton's law of universal gravitation reigned supreme, explaining the motions of planets and the dance of celestial objects with elegant precision. But Newton's theory, though powerful, lacked a crucial element: an understanding of light's relationship to gravity. This gap in understanding would set the stage for Michell and Laplace's revolutionary insights. John Michell, an English natural philosopher, astronomer and clergyman, possessed a mind that roamed freely across the cosmos. He was a true polymath, his interests spanning fields as diverse as geology, seismology, and even the design of scientific instruments. Yet it was his fascination with the heavens that would lead him to contemplate the unthinkable. In 1783, while pondering the implications of Newton's law of gravity, Michell conceived of a star so massive, so gravitationally potent, that its escape velocity would exceed the speed of light itself. Escape velocity, in essence, is the speed an object needs to achieve to break free from the gravitational pull of another, more massive object. For Earth, escape velocity is a brisk 7 miles per second. For the Sun, much more massive, it's a scorching 383 miles per second. But for Michell's hypothetical dark star, the escape velocity would surpass the cosmic speed limit, 186,000 miles per second, the speed of light. This meant that nothing, not even light, could escape the clutches of such a monstrous object. Michell reasoned that these dark stars, though invisible to the eye, could still exert a gravitational pull on nearby stars, betraying their presence through the subtle dance of celestial objects. Michell's idea, though groundbreaking, was purely theoretical. He lacked the mathematical tools and the observational evidence to fully develop his concept of dark stars. However, his work planted the seed of an idea that would continue to germinate in the minds of scientists for generations to come. Across the English Channel, a French mathematician named Pierre-Simon Laplace was independently arriving at a similar startling conclusion. Laplace, renowned for his work on celestial mechanics and probability, was deeply engrossed in the study of gravity and its implications for the cosmos. In 1796, Laplace published his seminal work, Exposition du système du monde, in which he explored the possibility of corps obscurs or dark bodies existing within the universe. Like Michel, Laplace reasoned that sufficiently massive stars could possess gravitational fields so intense that light itself would be unable to escape. Laplace, however, went a step further than Michel, employing his formidable mathematical prowess to calculate the size such a dark body would need to possess in order to trap light. He concluded that a star with the same density as the Sun, but with a diameter 250 times greater, would be invisible to distant observers. Despite their independent discoveries, both Michel and Laplace's ideas about dark stars were met with a mixture of intrigue and skepticism. The prevailing scientific understanding of light at the time was rooted in Newton's corpuscular theory, which depicted light as a stream of particles. The idea that these particles could be influenced by gravity, let alone trapped by it, seemed inconceivable to many. The scientific community, steeped in Newtonian physics and lacking the observational tools to detect such faint objects, largely relegated the concept of dark stars to the realm of mathematical curiosities. Michel and Laplace's ideas, though brilliant in their foresight, were simply ahead of their time. The 19th century witnessed a revolution in our understanding of light with the advent of James Clerk Maxwell's theory of electromagnetism. Maxwell's equations, published in 1865, elegantly unified electricity, magnetism, and light, demonstrating that light itself was an electromagnetic wave. This discovery further complicated the already perplexing question of light's interaction with gravity. The Newtonian framework, which had served as the bedrock of physics for centuries, was beginning to show its limitations. It could not adequately explain the behavior of light in the presence of strong gravitational fields, nor could it account for the strange anomalies that astronomers were beginning to observe in the motions of stars and galaxies. The universe, it seemed, held secrets that lay beyond the grasp of classical physics. A new theory, one that could reconcile gravity with the nature of light and space-time, was desperately needed. The stage was set for a revolution, one that would reshape our understanding of the cosmos and bring the whispers of dark stars back from the shadows. Despite the prevailing skepticism surrounding the existence of dark stars, their echoes persisted in the scientific literature. Astronomers, armed with increasingly powerful telescopes, began to observe phenomena in the cosmos that hinted at the presence of incredibly dense, compact objects lurking in the depths of space. Binary star systems, where two stars are locked in a gravitational dance around a common center of mass, provided tantalizing clues. In some of these systems, astronomers noticed that one star would exhibit unusual orbital behavior, as if being tugged upon by an unseen companion. These unseen companions, some theorized, could be the elusive dark stars predicted by Michel and Laplace. Furthermore, the discovery of X-rays in the late 19th century and the subsequent development of X-ray astronomy in the mid-20th century opened up new windows into the universe. Astronomers detected powerful X-ray sources emanating from certain regions of space, suggesting the presence of extremely hot and dense objects that defied explanation by conventional stellar models. These observations, though indirect, provided compelling evidence for the existence of objects far more compact and gravitationally powerful than any previously known. The whispers of dark stars, once dismissed as mere theoretical curiosities, were beginning to grow louder, demanding the attention of the scientific community. The dawn of the 20th century brought with it a seismic shift in our understanding of the universe. In 1905, a young Albert Einstein, working as a patent clerk in Bern, Switzerland, published his groundbreaking theory of special relativity. This revolutionary theory, with its elegant equation energy equals mass times the speed of light squared, shattered the Newtonian view of a static absolute universe, replacing it with a dynamic relative one where space and time were intertwined. But Einstein's revolution was far from over. He spent the next decade grappling with a far more challenging task, incorporating gravity into his relativistic framework. In 1915, after years of intense intellectual struggle, Einstein presented his masterpiece to the world, the theory of general relativity. General relativity, a triumph of human ingenuity, redefined gravity not as a force acting at a distance, but as a curvature of space-time caused by the presence of mass and energy. Einstein's equations, elegant in their simplicity yet profound in their implications, provided a new lens through which to view the cosmos, one that would ultimately illuminate the true nature of Michell and Laplace's dark stars. With the advent of general relativity, the stage was set for a new era of astrophysical exploration. The whispers of dark stars, once lost in the void of scientific uncertainty, were about to become a roar, heralding a revolution in our understanding of the most extreme objects in the universe.
Across the vast expanse of the cosmos, stars are born. They blaze with fiery brilliance, and ultimately, they meet their demise. While smaller stars, like our own sun, fade into white dwarfs at the end of their lives, massive stars, those many times heavier than our sun, are destined for a far more dramatic and violent fate. These stellar giants, fueled by the nuclear fusion in their cores, burn through their fuel reserves at a prodigious rate, their lives measured in millions, not billions of years. And when their internal furnaces finally sputter and die, these behemoths of the cosmos collapse under their own immense gravity, leaving behind remnants of unimaginable density and gravitational pull black holes. Imagine a star perhaps 30 times the mass of our sun, nearing the end of its stellar life. For millions of years it has shone brightly, a beacon in the cosmic darkness, its immense gravity holding sway over a retinue of planets and smaller stars. But the star's internal reserves of hydrogen, the fuel that sustains its nuclear fusion, are dwindling. The outward pressure generated by fusion, which once counterbalanced the inward pull of gravity, begins to falter. The star's core, once a furnace of unimaginable power, contracts under its own weight, its temperature and density soaring to incomprehensible levels. As the core collapses, the star's outer layers are no longer held in check. They come crashing down towards the center with unimaginable force, only to be met by the incredibly dense, compact core. The result is a cataclysmic rebound, a shockwave of unimaginable power that rips through the star, blasting its outer layers into space in a dazzling supernova explosion. For a brief, shining moment, the supernova outshines entire galaxies, a cosmic spectacle visible across billions of light-years. The fate of the stellar core, however, is far more enigmatic. If the core's remaining mass, the heart of the once mighty star, is sufficiently great, typically more than 3 times the mass of our sun, then no known force in the universe can halt its inexorable collapse. Gravity, now the undisputed master of the star's destiny, crushes the core with unrelenting force. Electrons are forced into protons, forming neutrons, and even these particles, once thought to be the fundamental building blocks of matter, are squeezed together until the core implodes into an infinitesimally small point, a singularity. The singularity, a point of infinite density and zero volume, lies at the heart of a black hole, a region of space-time where gravity reigns supreme, warping the very fabric of the cosmos. Surrounding the singularity is an invisible boundary known as the event horizon, a point of no return for anything that dares to venture too close. Once an object crosses the event horizon, its fate is sealed. Not even light, the fastest entity in the universe, can escape the black hole's gravitational clutches. This process of stellar collapse, from the death throes of a massive star to the formation of a black hole, is one of the most extreme and violent events in the universe. It is a testament to the power of gravity, the ultimate sculptor of the cosmos, to transform matter and energy into objects of unimaginable density and gravitational pull. Black holes, born from the ashes of stellar giants, are not merely cosmic curiosities, they are dynamic entities, their immense gravity influencing the evolution of galaxies and the very structure of the universe. In many ways, black holes are cosmic cauldrons, regions of intense activity where matter and energy are churned and transformed. As matter falls towards a black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees. This superheated material emits intense radiation, primarily in the X-ray portion of the electromagnetic spectrum. Furthermore, black holes can drive powerful jets of particles that travel at nearly the speed of light. These jets can interact with surrounding gas clouds, triggering star formation and influencing the evolution of entire galaxies. The discovery of black holes was a gradual unveiling, a series of observations and deductions. One of the earliest pieces of evidence for black holes came from the study of binary star systems. In the constellation Cygnus lies a binary star system known as Cygnus X1. This system, located about 6,000 light-years from Earth, consists of a blue supergiant star and an unseen companion. The blue supergiant is being actively stripped of its outer layers by its companion, forming a swirling accretion disk. However, the unseen companion, dubbed Cygnus X1, emits intense X-rays, far too energetic to be produced by any known type of star. Cygnus X1's mass, estimated to be about 15 times that of our Sun, is far too great to be a neutron star. The only plausible explanation was that Cygnus X1 was a black hole, its immense gravity stripping material from its companion star. This discovery, announced in 1972, provided the first strong observational evidence for the existence of black holes. Galactic architects. While stellar mass black holes are born from the death throes of individual stars, supermassive black holes are entities of a far grander scale. These cosmic behemoths, with masses ranging from millions to billions of times that of our Sun, play a pivotal role in the formation and evolution of galaxies. The presence of supermassive black holes was first hinted at by observations of active galactic nuclei, incredibly luminous objects at the centers of some galaxies. AGN emit vast amounts of energy across the electromagnetic spectrum, often outshining the combined light of all the stars in their host galaxies. The only known mechanism capable of powering such energetic objects is the accretion of matter onto supermassive black holes. As gas and dust spiral inward towards the event horizon of a supermassive black hole, they release gravitational potential energy, heating up to millions of degrees and emitting intense radiation. Supermassive giants enigma at the heart of galaxies. The existence of supermassive black holes raises intriguing questions about the early universe. These colossal objects, with masses equivalent to billions of suns, appear to have formed relatively early in cosmic history. How these behemoths grew so massive in such a short time frame remains one of the most perplexing mysteries in astrophysics. One theory suggests that supermassive black holes formed from the collapse of massive gas clouds in the early universe. These clouds could have collapsed directly into black holes, bypassing the star formation process altogether. Another possibility is that supermassive black holes formed through hierarchical mergers, starting with smaller black holes that gradually merged over billions of years. This process, driven by the gravitational interactions of galaxies, could explain the observed correlation between the masses of supermassive black holes and the masses of their host galaxies. The hunger of giants. Regardless of their origins, supermassive black holes continue to exert a profound influence on the galaxies they inhabit. Their immense gravity shapes the distribution of stars and gas, regulating star formation and influencing the overall evolution of their host galaxies. As matter falls towards a supermassive black hole, it releases vast amounts of energy, heating the surrounding gas and driving powerful outflows. These outflows, often observed as jets of particles traveling at nearly the speed of light, can interact with surrounding gas clouds, triggering star formation. In some cases, the energy released by accreting supermassive black holes can quench star formation altogether, creating red and dead galaxies. This delicate balance between the feeding of supermassive black holes and the evolution of their host galaxies highlights the complex and interconnected nature of the cosmos. In the cold, unforgiving vacuum of space, black holes stand as silent sentinels, their presence marked not by light but by its absence. These enigmatic objects, born from the death throes of massive stars, are regions where gravity's dominion is absolute. At the heart of every black hole lies a singularity, a point of infinite density and zero volume. Yet surrounding this singularity is a boundary, a point of no return known as the event horizon. Imagine for a moment that you are an intrepid space traveler, embarking on a perilous journey to the edge of a black hole. As you approach this cosmic monster, you would notice nothing particularly unusual at first. The stars would still twinkle in the distance, their light seemingly unaffected by the black hole's presence. Finally, you would reach the point of no return, the event horizon. This boundary, often depicted as a spherical surface surrounding the black hole, is not a physical barrier in the traditional sense. It is simply the point beyond which the black hole's gravity is so strong that escape becomes impossible, even for light itself. Once you cross the event horizon, your fate is sealed. No matter how powerful your engines, you would be drawn inexorably towards the singularity at the black hole's core. As you plunge deeper into the black hole, the relentless pull of gravity would begin to distort your spacecraft, stretching it out in a process known as spaghettification. This bizarre effect arises from the difference in gravitational pull across the length of your spacecraft. The event horizon, however, is more than just a point of no return. It is also a region where our understanding of space and time is pushed to its limits. Massive objects like stars and planets create depressions in the fabric of spacetime, much like a bowling ball placed on a trampoline. These depressions are what we perceive as gravity. Black holes, with their immense density and gravitational pull, create the most extreme distortions of spacetime imaginable. Near the event horizon, spacetime is so warped that the usual roles of space and time are reversed. Inside a black hole, the singularity doesn't lie in the future as it would in normal spacetime.
The ergosphere, a realm of paradox. For non-rotating black holes, the event horizon marks the point of no return. However, most black holes are thought to rotate, adding a further layer of complexity and intrigue. Rotating black holes possess an additional region of spacetime outside the event horizon known as the ergosphere. The ergosphere is a place where strange and counterintuitive phenomena can occur. Objects caught within the ergosphere are inevitably forced to rotate with the black hole. This effect, known as frame dragging, is a consequence of the black hole's immense angular momentum.
Hawking radiation black holes, not so black. For decades, black holes were thought to be inescapable cosmic sinks. However, in 1974, Stephen Hawking made a groundbreaking discovery that would forever change our understanding of these enigmatic objects. Hawking showed that black holes, contrary to popular belief, are not entirely black. Instead, they emit a faint thermal radiation, now known as Hawking radiation, due to quantum effects near the event horizon. According to quantum mechanics, empty space is filled with virtual particle-antiparticle pairs that constantly pop into existence and then annihilate each other. Hawking realized that if such a virtual particle pair were to be created near the event horizon of a black hole, one particle could fall into the black hole, while the other escaped to infinity. The escaping particle would carry away a small amount of energy from the black hole, effectively reducing its mass over time. The information paradox, a cosmic conundrum. Hawking's discovery of black hole evaporation raised a profound puzzle, the information paradox. According to quantum mechanics, information in the form of quantum states cannot be destroyed. This principle, known as unitarity, is fundamental to our understanding of the quantum world. However, the process of black hole evaporation seems to violate this principle. When a black hole forms, it swallows all the information about the matter that collapsed to create it. If the black hole evaporates completely via Hawking radiation, what happens to all the information that was trapped inside? The information paradox, far from being a mere theoretical curiosity, has profound implications for our understanding of the cosmos. It suggests that our current theories of gravity and quantum mechanics are incomplete and that a more fundamental theory, one that unifies these two pillars of modern physics, is needed to fully explain the nature of black holes and the universe itself. Physicists have proposed a number of possible solutions to the information paradox, each with its own set of intriguing implications. Some theories suggest that information is not truly lost inside a black hole, but is somehow encoded in subtle correlations within the outgoing Hawking radiation. Others propose that black holes do not evaporate completely, but leave behind remnants, tiny objects that preserve the information about the matter that fell into the black hole. The search for a solution to the information paradox has driven much of the progress in theoretical physics in recent decades. It has led to the development of string theory, a framework that attempts to unify all the fundamental forces of nature, including gravity, into a single coherent theory. It has also sparked new insights into the nature of quantum gravity, the elusive theory that would reconcile general relativity with quantum mechanics. For centuries, black holes remain shrouded in mystery, their existence inferred from indirect evidence, their true nature a subject of intense speculation. Astronomers, limited by the electromagnetic spectrum, could only observe the effects of black holes on their surroundings. The swirling accretion disks, the powerful jets of particles, the gravitational pull on nearby stars. But the black holes themselves, hidden behind their event horizons, remained elusive, their secrets locked away in the depths of space-time. However, a new era of astronomy was dawning, one that promised to unveil the invisible and reveal the secrets of these cosmic enigmas. This revolution was not driven by light, but by gravity itself, by the subtle ripples in the fabric of space-time that emanate from the most violent events in the universe, the collisions of black holes. These ripples, known as gravitational waves, were first predicted by Albert Einstein in 1916 as a consequence of his theory of general relativity. Einstein showed that massive objects, when accelerated, create disturbances in spacetime, much like a boat moving through water creates waves. These gravitational waves, however, are incredibly weak, far weaker than any other known force in the universe. Detecting them would require instruments of unprecedented sensitivity, instruments that could measure changes in distance smaller than the width of an atom. For decades, the search for gravitational waves remained a tantalizing dream, a quest pursued by a small but dedicated group of scientists who dared to challenge the technological limitations of their time. The challenge lay not only in the extreme faintness of gravitational waves but also in their unique nature. Unlike light waves, which are electromagnetic waves that travel through spacetime, gravitational waves are ripples in spacetime itself. Detecting them would be like listening to the universe breathe, sensing the subtle vibrations of the cosmic drum. In the 1970s, a team of physicists led by Rainer Weiss at MIT began developing a revolutionary new type of instrument designed specifically to detect gravitational waves. Their idea was deceptively simple, yet technologically daunting. Use lasers to measure the minute changes in distance between mirrors suspended kilometers apart. Any passing gravitational wave, they reasoned, would stretch and squeeze spacetime, causing the distance between the mirrors to fluctuate ever so slightly. This concept, known as laser interferometry, formed the basis for the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two identical detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana, separated by 3,000 kilometers. Each detector consists of two 4-kilometer-long arms arranged in an L shape, with mirrors suspended at the ends of each arm. Laser beams are bounced back and forth between the mirrors, and their interference patterns are carefully monitored for any telltale signs of a passing gravitational wave. Listening to the cosmos. The construction of LIGO was a monumental undertaking, a testament to human ingenuity, and the relentless pursuit of scientific knowledge. It took decades of research and development, countless hours of engineering and construction, and the unwavering dedication of hundreds of scientists and engineers to bring LIGO to fruition. Finally, in 2002, LIGO began its first science run, its sensitive detectors poised to listen to the whispers of gravity from the distant universe. For years, LIGO listened patiently, its detectors humming with anticipation, but the cosmos remained silent. No gravitational waves were detected, and some began to doubt whether these elusive ripples in space-time would ever be found. However, the LIGO team persevered, constantly upgrading their instruments, improving their sensitivity, and refining their data analysis techniques. Their persistence would be rewarded. In 2015, after a major upgrade that significantly enhanced LIGO's sensitivity, the detectors finally captured what they had been searching for: the faint but unmistakable signature of a gravitational wave. The signal, a brief chirp lasting only a fraction of a second, arrived first at the Livingston detector, and then, 7 milliseconds later, at the Hanford detector, confirming that it originated from a distant cosmic source. Cosmic Symphony of Destruction. The source of the gravitational waves, astronomers determined, was a pair of black holes, each about 30 times the mass of our Sun, locked in a death spiral billions of light-years away. As the black holes orbited each other, their immense gravity warped space-time, radiating energy away in the form of gravitational waves. This loss of energy caused the black holes to spiral closer and closer together, their orbital speed increasing until they finally collided in a cataclysmic merger, releasing more energy in that brief instant than all the stars in the observable universe combined. The gravitational waves from this cosmic collision, traveling at the speed of light, spread out through the universe like ripples from a stone dropped in a pond. After traveling for over 1 billion years, these faint echoes of a long-ago cataclysm reached Earth, where they were captured by LIGO's sensitive detectors, marking a pivotal moment in the history of astronomy. The detection of gravitational waves from merging black holes not only confirmed a key prediction of Einstein's theory of general relativity, but also provided the first direct evidence for the existence of these elusive objects. Furthermore, it opened up an entirely new way of observing the universe, one that did not rely on light but on the very fabric of space-time itself. Capturing the Shadow of Infinity. The groundbreaking detection of gravitational waves by LIGO in 2015 heralded a new era of astronomy, one in which we could listen to the whispers of gravity from the most extreme events in the universe. But astronomers were not content with merely listening to the cosmos. They yearned to see the invisible, to capture an image of a black hole, the most enigmatic object in the universe. This dream, once thought to be impossible, became a reality thanks to the Event Horizon Telescope, EHT, a global network of radio telescopes linked together to create a virtual telescope the size of Earth. The EHT's target was Sagittarius A*, a supermassive black hole lurking at the center of our Milky Way galaxy, about 26,000 light-years from Earth. Observing Sagittarius A* is a daunting task. Despite its immense mass, equivalent to about 4 million suns, the black hole itself is incredibly small, about 44 million kilometers across, or roughly the size of Mercury's orbit around the Sun. Furthermore, it is shrouded by a thick cloud of gas and dust, obscuring it from view at visible wavelengths. To overcome these challenges, the Event Horizon Telescope observes Sagittarius A* at radio wavelengths which can penetrate the obscuring gas and dust. By combining data from multiple telescopes around the world, the EHT creates a virtual telescope with an angular resolution sharp enough to resolve the black hole's event horizon, the point of no return for light and matter. In April 2019, after years of planning, observation, and data analysis, the EHT team unveiled the first-ever image of a black hole, a stunning achievement that captivated the world and ushered in a new era of black hole astrophysics. The image, a testament to the power of human ingenuity and international collaboration, shows a bright ring of light surrounding a dark central region, the black hole's shadow. The bright ring arises from the superheated gas and dust orbiting the black hole at nearly the speed of light. As this material swirls around the black hole, it emits radio waves that are lensed and distorted by the black hole's intense gravity, creating the observed ring-like structure. The dark central region, the black hole's shadow, is a region of spacetime so warped by gravity that not even light can escape. Its size and shape are consistent with the predictions of Einstein's theory of general relativity, providing further confirmation of this groundbreaking theory in the most extreme gravitational environment yet observed. The EHT's image of Sagittarius A** is more than just a stunning visual. It provides a wealth of information about the black hole's properties, such as its mass, spin, and orientation. By studying the details of the bright ring and the dark shadow, astronomers can learn about the behavior of matter and light in the presence of extreme gravity, testing the limits of our current understanding of physics. The era of black hole astronomy has just begun. With new telescopes and instruments coming online, we are poised to unravel the mysteries of these enigmatic objects in unprecedented detail. From the echoes of gravitational waves to the shadows of event horizons, black holes continue to captivate our imaginations, reminding us of the vastness of the cosmos and the boundless capacity of human curiosity. From the earliest whispers of dark stars to the groundbreaking images captured by the Event Horizon Telescope, the story of black holes is a testament to the enduring power of human curiosity and our relentless pursuit of knowledge. For centuries, these enigmatic objects have captivated our imaginations, challenging our understanding of the cosmos and pushing the boundaries of theoretical physics. What began as a series of thought experiments, a contemplation of gravity's ultimate dominion, has blossomed into a vibrant field of research, fueled by technological advancements and the collective efforts of scientists around the world. The journey that led us to our current understanding of black holes has been marked by both moments of profound insight and periods of frustrating uncertainty. From John Michell's initial conception of dark stars to Albert Einstein's revolutionary theory of general relativity, which provided the theoretical framework for understanding black holes, each step forward has been a testament to the power of human ingenuity to unravel the secrets of the universe. The discovery of Cygnus X1, a binary star system harboring a stellar mass black hole, provided the first concrete evidence that these objects were not merely theoretical constructs but existed in the real universe. The subsequent development of X-ray astronomy opened up a new window into the cosmos, revealing the presence of supermassive black holes lurking at the hearts of galaxies, their immense gravitational pull shaping the evolution of these cosmic behemoths. Uncharted territories. Despite these remarkable advancements, our journey into the realm of black holes is far from over. In many ways, we have only just begun to scratch the surface of these enigmatic objects, our understanding limited by the current boundaries of our knowledge and the technological capabilities of our instruments. Yet, with each new discovery, each tantalizing glimpse into the depths of spacetime, new questions arise, beckoning us to venture further into the unknown. The detection of gravitational waves by LIGO and Virgo, a testament to the power of human ingenuity to measure the most subtle vibrations of the cosmos, has opened up an entirely new avenue for studying black holes. These ripples in spacetime, generated by the most violent events in the universe, carry with them encoded information about the objects that created them, their masses, spins, and even their compositions. As our ability to detect and analyze gravitational waves improves, we can expect a symphony of cosmic signals, revealing the hidden mergers of black holes and neutron stars throughout the universe. These observations will provide invaluable insights into the formation and evolution of these extreme objects, shedding light on the processes that govern the dynamics of the cosmos. Black holes, once thought to be isolated oddities, are now recognized as integral components of the cosmic tapestry, their influence extending far beyond their immediate surroundings. They play a pivotal role in the evolution of galaxies, regulating star formation, shaping the distribution of matter, and even influencing the large-scale structure of the universe. Supermassive black holes lurking at the centers of most galaxies are thought to have played a crucial role in the formation and evolution of their host galaxies. Their immense gravitational pull draws in surrounding gas and dust, fueling their growth and triggering bursts of star formation. The energy released during these accretion processes can heat up the surrounding gas to millions of degrees, driving powerful outflows that can influence star formation rates across entire galaxies. Furthermore, black holes are thought to play a role in the distribution of dark matter, the invisible substance that makes up the majority of the mass in the universe. The gravitational pull of black holes can act as seeds for dark matter halos, the vast invisible structures that envelop galaxies and influence their interactions with one another. Perhaps the most profound questions surrounding black holes lie at the intersection of general relativity and quantum mechanics, two of the most successful theories in physics, yet inherently incompatible with each other. General relativity describes the universe on the largest scales, the realm of stars, galaxies, and the fabric of space-time itself. Quantum mechanics, on the other hand, governs the universe on the smallest scales, the realm of atoms, subatomic particles, and the bizarre rules that govern their behavior. The singularity at the heart of a black hole, a point of infinite density and zero volume, represents a breakdown of general relativity, a point where our current understanding of physics crumbles. It is here, at the boundary of the infinitely small, where quantum effects are thought to become dominant, potentially offering a glimpse into the quantum nature of gravity. The information paradox, the question of what happens to information that falls into a black hole, highlights the clash between these two fundamental theories. While general relativity suggests that information is lost forever inside a black hole, quantum mechanics dictates that information cannot be destroyed. The quest to understand black holes is ultimately a quest to understand the universe itself, its origins, its evolution, and its ultimate fate. These enigmatic objects, once relegated to the realm of science fiction, have emerged as cosmic laboratories, testing the limits of our knowledge and pushing us to develop new theories and technologies to probe the depths of the cosmos. The future of black hole research is bright, filled with the promise of new discoveries and the potential to revolutionize our understanding of the universe. New telescopes and instruments, both on Earth and in space, will provide us with unprecedented views of black holes, revealing their secrets in greater detail than ever before. We can expect to witness the birth of black holes in real time, observing the death throes of massive stars as they collapse into these cosmic abysses. We will map the distribution of black holes throughout the universe, tracing their evolution over cosmic time and unraveling their role in the formation of galaxies and the large-scale structure of the cosmos. The story of black holes is a story of exploration, discovery, and the boundless capacity of the human spirit to unravel the mysteries of the universe. It is a story that transcends generations, inspiring awe and wonder in all who dare to gaze up at the night sky and contemplate the profound implications of these cosmic enigmas. As we continue our journey into the realm of black holes, we embark on a voyage of discovery, not only of the cosmos but also of ourselves, our place in the universe, and the limits of our understanding. It is a journey filled with challenges, setbacks, and moments of profound revelation, a journey that reminds us that the universe is far stranger, far more wondrous, and far more awe-inspiring than we could ever have imagined. The quest to understand black holes is an invitation to explore, to question, and to marvel at the intricate workings of the universe. It is a reminder that we live in a universe of infinite possibilities, a universe where the boundaries of knowledge are constantly expanding, and where the greatest discoveries may yet lie ahead. From the moment humans first gazed upon the night sky, we've been captivated by the cosmos. The twinkling stars, distant planets, and ethereal glow of the Milky Way have sparked our imaginations for millennia.
We've created myths and legends, built telescopes, and launched spacecraft, all in pursuit of understanding the celestial tapestry above us.
Our universe is a place of extraordinary beauty and mind-boggling scale. It's a realm of swirling galaxies, fiery nebulae,
and celestial objects that defy our everyday experience. Yet, for all its splendor, the universe also harbors secrets, places where the laws of physics as we know them are pushed to their limits.
These are the cosmic abysses, the enigmatic black holes. Black holes stand as a testament to the immense power of gravity.
A force so fundamental that it shapes the cosmos itself. These celestial objects are born from the death throes of massive stars,
collapsing under their own weight until they vanish from sight, leaving behind a region of space-time so warped that nothing, not even light, can escape their grasp.
In this exploration, we embark on a journey into the heart of these cosmic enigmas, venturing into the darkest corners of the universe to confront the most terrifying black holes known to science.
Prepare to have your perceptions of reality challenged as we delve into the mysteries of these gravitational behemoths. Black holes are perhaps the most intriguing and perplexing objects in the universe.
They are regions of space-time where gravity's pull is so intense that nothing, not even light, can escape their grasp. This phenomenon arises from the extreme warping of space-time caused by an incredibly dense mass concentrated within a tiny region.
Imagine, if you will, taking our entire planet, the Earth, with all its mountains, oceans, and teeming life, and squeezing it down to the size of a marble.
That's the kind of density we're talking about with a black hole. At such extreme densities, the fabric of space-time becomes so distorted that it creates a gravitational well from which nothing can climb out.
The boundary of a black hole is defined by its event horizon, a point of no return beyond which escape from the black hole's gravitational pull is impossible.
Anything that crosses this boundary, whether it's a spaceship, a planet, or even light itself, is inexorably drawn inward, destined to be consumed by the singularity at the black hole's core.
This singularity is a point of infinite density, a place where the laws of physics as we understand them break down.
It's a realm of mystery and speculation, a cosmic abyss that continues to challenge our understanding of the universe.
Black holes are not merely theoretical constructs, they're very real objects that populate our universe. Astronomers have identified countless black holes, ranging in size from a few times the mass of our Sun to supermassive black holes billions of times heavier, lurking at the centers of galaxies.
The existence of black holes is supported by a wealth of observational evidence. We see stars orbiting invisible companions with incredible speeds, indicating the presence of an unseen massive object, a black hole. We observe jets of superheated matter spewing from galactic centers, powered by the immense gravitational energy of supermassive black holes.
Black holes challenge our understanding of physics in profound ways. At the event horizon, time itself slows down, and at the singularity, it is believed to stop altogether. The concepts of space and time, so fundamental to our everyday experience, become intertwined and distorted in the presence of these gravitational behemoths.
The study of black holes pushes the boundaries of our knowledge, forcing us to confront the limitations of our current understanding of the universe. These cosmic abysses serve as cosmic laboratories, offering tantalizing glimpses into the nature of gravity, space-time, and the fundamental laws that govern our cosmos.
In this series, we embark on a thrilling journey to explore some of the most terrifying black holes in the known universe.
Our exploration will take us across vast cosmic distances, from our own Milky Way galaxy to the farthest reaches of the observable universe.
We'll encounter black holes of unimaginable size and power, each with its unique story to tell.
We'll delve into the science behind these enigmatic objects, unraveling the mysteries of their formation, their properties, and their impact on the surrounding cosmos.
Our journey will be one of both scientific discovery and cosmic horror.
We'll witness the terrifying power of black holes as they devour stars, warp space-time, and shape the destinies of entire galaxies.
So fasten your seatbelts and prepare for a thrilling ride as we venture into the heart of darkness, exploring the universe's most terrifying black holes. Beyond the veil-unraveling cosmic horrors, our exploration begins with an understanding of what makes black holes so terrifying.
It's not just their immense gravity or their ability to trap light that sends shivers down our spines. It's the very concept of a singularity, a point of infinite density where the laws of physics break down, that truly captures our imagination and ignites our primal fears.
Imagine being drawn inexorably towards a black hole, the pull of gravity intensifying with each passing moment. As you approach the event horizon, you'd witness the universe around you distort and warp, time itself seeming to slow to a crawl.
If you were to cross the event horizon, there would be no turning back. You'd be stretched and squeezed by the intense tidal forces, a process known as spaghettification, until you were ultimately consumed by the singularity, your very essence crushed out of existence.
But the terror of black holes extends beyond their individual power. These cosmic behemoths can have cataclysmic effects on their surroundings, shaping the evolution of galaxies, triggering star formation, and even influencing the large-scale structure of the universe.
Join us as we journey beyond the veil of the unknown, unraveling the cosmic horrors that lurk within these gravitational abysses.
Cosmic crunch, the birth of a black hole. Black holes are born from the violent deaths of massive stars.
When a star exhausts its fuel, gravity causes its core to collapse. This collapse forms a singularity, creating a black hole.
The outer layers explode in a supernova, but the core remains.
This process showcases the immense power of gravity.
Event horizon, point of no return. At the heart of every black hole lies the event horizon, a boundary in space-time beyond which gravity's grip is so strong that nothing, not even light, can escape.
Imagine a vast cosmic drain, its pull so powerful that anything that ventures too close is swept away, never to be seen again. The event horizon is not a physical barrier like the surface of a planet. It's a region where the very fabric of space-time is warped beyond recognition.
As you approach the event horizon, time itself would seem to slow down from your perspective. If you were to shine a beam of light towards the event horizon, it would appear to redshift, its wavelength stretching out as it loses energy trying to escape the black hole's gravitational pull.
Crossing the event horizon would be a one-way trip. Once you've crossed this boundary, there is no turning back.
You would be inexorably drawn towards the singularity at the black hole's center, your fate sealed by the unyielding force of gravity. The event horizon is a stark reminder of the limits of our understanding of the universe.
It's a place where our everyday notions of space, time, and reality itself break down, swallowed by the abyss of the black hole.
Spaghettification, the ultimate cosmic stretch. One of the most terrifying aspects of black holes is the phenomenon of spaghettification, a process that stretches and compresses objects that fall into them.
This cosmic stretching occurs due to the extreme tidal forces present near a black hole's event horizon. Imagine yourself falling feet first towards a black hole. As you approach the event horizon, the gravitational pull on your feet would be significantly stronger than the pull on your head.
This difference in gravitational force would stretch your body like a piece of cosmic taffy in a process aptly named spaghettification. But spaghettification doesn't stop there.
As you continue to fall towards the singularity, the tidal forces would become so extreme that they would compress your body horizontally, squeezing you from the sides. The result would be a long, thin strand of matter, stretched and compressed beyond recognition.
While spaghettification might seem like the stuff of science fiction, it's a very real consequence of the extreme gravitational gradients near black holes. It's a gruesome reminder of the immense power of these cosmic objects and the bizarre effects they can have on matter. Supermassive giants, lords of the galactic dance. While stellar mass black holes formed from the collapse of massive stars are terrifying in their own right, they pale in comparison to their supermassive cousins.
These gravitational behemoths, millions or even billions of times the mass of our Sun, lurk at the centers of galaxies, including our own Milky Way. Supermassive black holes are thought to have played a crucial role in the evolution of galaxies.
Their immense gravity can draw in vast amounts of gas and dust, creating accretion disks that swirl around them like cosmic whirlpools.
These accretion disks can be incredibly hot and luminous, emitting intense radiation across the electromagnetic spectrum. As matter spirals into a supermassive black hole, it releases tremendous amounts of energy, powering some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei.
These objects can outshine entire galaxies, their brilliance visible across vast cosmic distances. Supermassive black holes are not merely passive bystanders in the cosmic drama.
They are active participants, shaping the destinies of galaxies and influencing the large-scale structure of the universe.
Quasars, beacons of cosmic destruction. Among the most awe-inspiring and terrifying objects in the universe are quasars, incredibly luminous and distant objects powered by supermassive black holes.
The name quasar is short for quasi-stellar radio source, reflecting their early discovery as point-like sources of radio waves. Quasars are thought to be powered by the accretion of matter onto supermassive black holes at the centers of distant galaxies.
As matter falls into the black hole's gravitational grasp, it forms a swirling accretion disk, heated to millions of degrees by friction and gravitational forces.
This superheated disk emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays.
Quasars are among the most luminous objects in the universe.
Some shining with the brilliance of trillions of suns.
They are also incredibly distant, with some lying billions of light-years away.
This means that the light we see from them today was emitted when the universe was very young, offering us a glimpse into the early cosmos.
The sheer power of quasars is both awe-inspiring and terrifying.
These objects are capable of releasing unimaginable amounts of energy, dwarfing the output of even the most powerful stars.
They are a testament to the awesome power of gravity and the extreme conditions that can exist in the universe. The black hole paradox, where information disappears. Black holes present us with a profound paradox, a challenge to our understanding of the fundamental laws of physics.
This paradox arises from the fact that black holes seem to violate a fundamental principle of quantum mechanics, the conservation of information. According to quantum mechanics, information cannot be destroyed.
This means that the information about the state of a system, such as the position and momentum of its particles, is always conserved, even if the system undergoes a transformation. However, black holes seem to defy this principle.
When matter falls into a black hole, it is believed to be crushed out of existence at the singularity. This would seem to imply that the information about the state of that matter is also destroyed, violating the principle of information conservation.
This is known as the black hole information paradox. The black hole information paradox has puzzled physicists for decades, leading to numerous attempts to reconcile the seemingly contradictory principles of general relativity and quantum mechanics. It remains one of the most intriguing and challenging problems in modern physics, pushing the boundaries of our understanding of the universe. TON 618, a beacon from the early universe. Our journey begins with TON 618, a quasar so luminous it outshines entire galaxies. Powered by a supermassive black hole, its mass is over 66 billion times that of our Sun. If placed in our solar system, its event horizon would extend beyond Pluto. The light we see from TON 618 has traveled over 10 billion years to reach us. Unfathomable scale, the reign of TON 618. The sheer scale of TON 618 is difficult to comprehend.
Its black hole is so massive that it boggles the mind, defying our everyday experience of gravity and the nature of reality. Imagine the combined mass of billions of stars, all crushed together into a region of space smaller than our solar system.
The gravitational pull of TON 618's black hole is so strong that it can rip apart entire stars, devouring their matter and adding to its already immense mass. As matter spirals into the black hole, it forms an accretion disk, a swirling vortex of superheated gas and dust that can span hundreds of thousands of light-years across.
The accretion disk of TON 618 is thought to be incredibly turbulent and chaotic, with matter colliding at near light speeds, generating intense friction and heat. This superheated disk emits radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, making TON 618 one of the most luminous objects in the universe.
The discovery of TON 618 and other supermassive black holes has forced astronomers to rethink their models of galaxy formation and evolution. It's now believed that these cosmic giants play a crucial role in shaping the destinies of galaxies, influencing star formation, and driving the evolution of the universe itself. The Cosmic Waltz introducing OJ-287. OJ-287 is a blazar located 3.5 billion light-years away, featuring a binary system of two supermassive black holes.
The larger black hole is 18 billion solar masses, while the smaller is 150 million. Their gravitational dance offers insights into the dynamics of extreme environments and the nature of gravity.
OJ-287 exemplifies the power of astronomy to explore the universe's most extreme corners. A dance of destruction. OJ-287's binary system. The orbital dance of OJ-287's black holes is not a graceful waltz but a violent tango. a cosmic clash of titans that sends shockwaves through space-time.
The smaller black hole orbits the larger one every 12 years, its path taking it through the accretion disk of its more massive companion. As the smaller black hole plunges through the accretion disk, it creates a shockwave that heats the surrounding gas to millions of degrees.
This superheated gas emits a burst of radiation across the electromagnetic spectrum, creating a flare that can be observed from Earth.
These flares are not just random events. They occur with remarkable regularity, providing astronomers with a unique opportunity to study the dynamics of this binary system.
The interaction between the two black holes in OJ 287 is not limited to these periodic flares. The immense gravitational forces at play are constantly warping and distorting the fabric of space-time, creating ripples known as gravitational waves that propagate outwards at the speed of light.
These gravitational waves carry with them information about the masses, spins, and orbital parameters of the black holes, providing astronomers with a unique tool to study these enigmatic objects and test the predictions of Einstein's theory of general relativity.
Predicting the unpredictable OJ 287's clockwork flares. One of the most intriguing aspects of OJ 287 is the predictability of its flares. Despite the chaotic and violent nature of this binary black hole system, the smaller black hole's passage through the accretion disk occurs with remarkable regularity, allowing astronomers to predict these events with impressive accuracy. This predictability has allowed astronomers to study OJ 287 in great detail, using a variety of telescopes and instruments to observe the flares across the electromagnetic spectrum. These observations have provided valuable insights into the properties of the black holes, the dynamics of their interaction, and the behavior of matter in extreme gravitational fields. The predictability of OJ 287's flares is a testament to the power of general relativity, Einstein's theory of gravity, which has been remarkably successful in explaining the behavior of these extreme systems. It's a reminder that even in the most chaotic and unpredictable environments, the laws of physics still hold sway. The study of OJ 287's flares has also played a crucial role in the development of techniques to detect gravitational waves, ripples in space-time predicted by Einstein's theory. By precisely measuring the timing of these flares, astronomers were able to refine their models of the binary system and improve their predictions for the strength and frequency of the gravitational waves it emits. The cosmic dance of OJ 287's black holes is not destined to last forever. As the two black holes orbit each other, they lose energy through the emission of gravitational waves, causing their orbit to shrink over time.
This process will eventually lead to a cataclysmic event, the merger of the two black holes into a single, even more massive object.
When these two behemoths finally collide, it will be one of the most energetic events in the history of the universe, releasing more energy in a fraction of a second than all the stars in the observable universe combined.
This energy will be released in the form of gravitational waves, sending ripples through the fabric of space-time that will propagate outwards at the speed of light.
The merger of OJ 287's black holes is not just a theoretical prediction, it's an inevitability, dictated by the laws of physics.
Astronomers estimate that this event will occur within the next 10,000 years, a blink of an eye on cosmic timescales.
The detection of gravitational waves from such a merger would be a landmark event in astronomy, providing unprecedented insights into the nature of gravity, the behavior of matter in extreme conditions, and the evolution of the universe itself. The merger of OJ 287's black holes will not just be a spectacular light show, it will also be a symphony of gravitational waves, ripples in the fabric of space-time that will carry with them the echoes of this cataclysmic event. These gravitational waves will be incredibly faint by the time they reach Earth, but their detection is within the capabilities of current and future gravitational wave observatories such as LIGO, Virgo, and the upcoming LISA mission. These observatories are designed to detect the minute distortions in space-time caused by the passage of gravitational waves, providing us with a new window into the universe. The detection of gravitational waves from OJ 287's merger would not only confirm our understanding of these extreme systems, but also provide a wealth of information about the properties of the merging black holes, such as their masses, spins, and the orientation of their orbit. This information would be invaluable for testing the predictions of general relativity and the strong gravity regime, where the gravitational fields are so intense that they can warp spacetime itself. It would also provide clues about the formation and evolution of supermassive black holes like those found in OJ 287, shedding light on the early universe and the processes that shaped the cosmos as we know it today. For centuries, black holes existed as theoretical constructs, mathematical curiosities predicted by Einstein's theory of general relativity, but never directly observed. That all changed in 2019 when the Event Horizon Telescope (EHT) collaboration achieved a groundbreaking feat, capturing the first-ever image of a black hole.
The target of this historic observation was M87*, the supermassive black hole lurking at the heart of the giant elliptical galaxy Messier 87, located some 55 million light-years away from Earth. M87* is a true cosmic heavyweight, with a mass estimated to be 6.5 billion times that of our Sun.
The image captured by the EHT wasn't a direct view of the black hole itself, as that would be impossible given that black holes trap light. Instead, the image revealed the black hole's shadow, a dark region silhouetted against the backdrop of the glowing accretion disk of hot gas and dust swirling around it.
This groundbreaking image provided the most direct evidence yet for the existence of black holes, and confirmed many of the predictions of general relativity, further solidifying Einstein's theory as one of the cornerstones of modern physics. It was a testament to the ingenuity and collaboration of scientists worldwide, pushing the boundaries of what's possible in observational astronomy.
Peering into the abyss, the Event Horizon Telescope. The Event Horizon Telescope is not a single telescope but rather a global network of radio telescopes, scattered across continents, working in unison to create a virtual telescope the size of Earth.
This technique, known as Very Long Baseline Interferometry, or VLBI, combines the signals from multiple telescopes to achieve an angular resolution far greater than any single telescope could achieve alone. To capture the image of M87*, the EHT team coordinated observations from 8 radio telescopes located in Chile, Hawaii, Arizona, Mexico, Spain, and Antarctica.
The data collected from these telescopes, amounting to petabytes of information, was then meticulously combined and analyzed using sophisticated algorithms to produce the final image.
The EHT's success in imaging M87* was a tour de force of both engineering and scientific collaboration. It required overcoming numerous technical challenges, including synchronizing the telescopes with atomic clocks, accounting for atmospheric distortions, and developing novel data processing techniques.
The EHT collaboration continues to observe M87* and other supermassive black holes, aiming to capture even sharper images and study the dynamics of these extreme environments in greater detail. Their work promises to further revolutionize our understanding of black holes, gravity, and the nature of the universe itself. Galactic architects, black holes, and galaxy evolution. Black holes shape galaxies, influencing their growth and structure.
They can be both creators and destroyers, driving feedback mechanisms.
Supermassive black holes accrete gas and dust, forming accretion disks.
Active galactic nuclei can outshine entire galaxies, releasing energy.
This feedback can also trigger star formation.
Jets from AGN can lead to bursts of star formation.
This balance regulates galaxy growth over cosmic time. Studying black holes helps us understand galaxy evolution.
Unraveling this interplay reveals the forces shaping the universe.
NGC 1277, a relic of the early universe. NGC 1277, a small galaxy in Perseus, harbors a supermassive black hole, making up 14% of its mass. This relic galaxy formed in the early universe and remains largely unchanged. Its study offers insights into early galaxy formation and black holes. A starving giant, the mystery of NGC 1277's black hole. Despite its enormous size, the supermassive black hole at the heart of NGC 1277 is surprisingly quiet.
Unlike most active galactic nuclei, NGC 1277's black hole is relatively inactive, earning it the nickname the starving giant. This lack of activity is puzzling, given the black hole's immense size and the abundance of gas and dust in the galaxy's central region.
Astronomers propose that the black hole has consumed most available material, or that gas and dust are prevented from falling in.
Further observations are needed to unravel the mystery of its inactivity.
IC 1101, the Colossus of the Cosmos. Located over 1 billion light-years away in the constellation Serpens,
IC 1101 is one of the largest known galaxies, dwarfing our Milky Way. IC 1101's central black hole is among the most massive ever detected, showcasing gravity's immense power to shape the cosmos.
Section 7, A Sea of Stars, Unraveling the Secrets of IC 1101.
IC 1101's growth likely involved hierarchical merging, where smaller galaxies collide and merge over billions of years.
This process has resulted in one of the largest known galaxies in the universe, a true cosmic giant.
Rogue black holes, cosmic wanderers in the night. These cosmic wanderers, known as rogue black holes, are remnants of disrupted galaxies ejected by gravitational interactions. Their existence challenges our understanding of galaxy evolution and the distribution of matter in the cosmos. XTEJ 1118 plus 480, a runaway black hole.
This binary system's high velocity suggests it was ejected from its birthplace, likely a star cluster, millions of years ago. The study of XTEJ 1118 plus 480 provides insights into the dynamics of black holes and the evolution of star clusters.
The threat from within rogue black holes in the Milky Way.
Estimates for the number of rogue black holes in our galaxy vary widely, their presence largely hidden until they interact with their surroundings.
The gravitational pull of a passing rogue black hole could distort the orbits of planets, sending them spiraling inward or flinging them into interstellar space.
These interactions can have catastrophic consequences for any planetary systems in their path.
Our journey into the realm of black holes culminates with a pilgrimage to the heart of our own galaxy, the Milky Way, where a supermassive black hole, known as Sagittarius A*, reigns supreme. Astronomers have been tracking the movements of stars for decades, revealing the presence of an unseen object of incredible mass. Studying Sagittarius A* provides us with a unique opportunity to test the laws of physics in extreme environments. Despite its proximity to Earth,
Sagittarius A* has proven to be a challenging object to study. By observing radio emissions, astronomers have been able to study the properties of Sagittarius A's accretion disk.
the universe is a dynamic and ever-evolving cosmic arena where galaxies collide, stars explode, and black holes merge in cataclysmic events.
These mergers release more energy in a fraction of a second than all the stars in the observable universe combined. By studying these events, we gain a deeper understanding of the history of the universe and the forces that shaped the cosmos.
As we emerge from our journey into the hearts of darkness, we carry with us a sense of awe and humility.
We've peered into the abyss, confronting the limits of our understanding of space, time, and the nature of reality itself.
Amidst the terror and awe,
We've also glimpsed a strange beauty, a cosmic ballet of creation and destruction.
guardians of the cosmic order, black holes have emerged as architects of the cosmos, shaping the evolution of galaxies and driving star formation.
We've explored the intricate dance of binary black hole systems, leading to inevitable mergers that send ripples through space-time.
Our exploration of black holes has been a journey of discovery, but it's also a reminder of how much we still don't know about the universe.
Each new observation raises more questions than answers, pushing the boundaries of our knowledge.
With each new discovery, we gain a deeper appreciation for the complexity and wonder of the cosmos. Our place in the cosmic ballet. As we reflect on the awe-inspiring power and enigmatic nature of black holes, it's natural to feel a sense of insignificance, our everyday lives dwarfed by the cosmic scales involved.
Yet, it's also an opportunity to gain a new perspective on our place in the grand scheme of things. We are, after all, children of the stars. Our very existence intertwined with the life cycles of stars and the cosmic processes that create and destroy them.
The atoms that make up our bodies were forged in the nuclear furnaces of stars, scattered across the cosmos by supernova explosions, and recycled through countless generations of stars and galaxies.
Black holes, for all their terrifying power, are an integral part of this cosmic cycle. their influence shaping the evolution of galaxies and the distribution of matter and energy throughout the universe.
In a sense, we owe our existence to these cosmic giants, for without them, the universe as we know it would not exist.
So, the next time you gaze up at the night sky, let your mind wander to the distant corners of the cosmos, to the black holes that lurk there, both terrifying and beautiful, reminders of the vastness and wonder of the universe we are privileged to call home.
Keep looking up. Our exploration of the universe's most terrifying black holes has been a journey into the unknown, a testament to the power of human curiosity and our relentless pursuit of knowledge.
But it's not the end of the story. It's just the beginning. As astronomers continue to peer deeper into the cosmos with ever more powerful telescopes and instruments, we can expect even more astonishing discoveries.
New insights into the nature of black holes and a deeper understanding of the universe we inhabit.
The quest to unravel the mysteries of the cosmos is a never-ending journey, one that will continue to inspire and challenge us for generations to come.
So keep looking up at the night sky, let your curiosity guide you.
And never lose your sense of wonder. The universe, with all its mysteries and wonders, awaits those who dare to explore its depths.
Thank you for joining us on this journey into the heart of darkness. We hope it has inspired you to learn more about the universe we inhabit and our place within its grand cosmic tapestry. Until next time, keep exploring, keep questioning, and keep looking up. We hope our voyage into the dark hearts of these monsters has inspired both awe and curiosity. If you enjoyed this deep dive into the most horrifying black holes in the universe, be sure to like, subscribe, and hit the notification bell so you never miss an adventure. Your support powers our channel, enabling us to journey deeper into space's most guarded secrets. Thank you for watching, and until next time, stay curious.